Okay, welcome everybody to my ZUCCMAP talk on data-driven discovery of scientific equations, titled How AI Finds the Few Variables That Control Everything, which is kind of a clickbait title. We're not explaining everything today. But the first part of the title is actually true. We will be using AI tools, and we will attempt to distill data down to the simplest possible description in as few variables as possible to make the data easier to deal with or to understand. First of all, a very brief historical note on how physical laws are generally discovered. So usually you have some data from observation or experiments, you come up with a hypothesis, you gather more evidence. Obviously, you need to use your physicist's intuition and prior knowledge. And the prime example of this is Kepler's laws. Kepler had very detailed astronomical observations, and through this process of the scientific method, he was able to find his equations that, as it turned out, fit this data very well. And nowadays, two things stand out. We have a lot of data, for example, meteorological data, which was talked about in last week's talk. And we have loads of computing power. And the question naturally arises how we might use computers and AI to make sense of these big data amounts from physical systems. So the basic problem that most physical discovery looks like is this: finding a function that fits given data. Obviously, this is ubiquitous. This is basically the main idea of machine learning. But if in machine learning you would train a neural network, you would get kind of a black box. It's a function that gives the outputs you desire, but you don't know anything about the structure, or it's hard to explain the structure at least. And a physical law needs to be simple, so most things, even the most complicated phenomena, can be described in just a few terms, and you want to be able to interpret it. This is kinetic energy, this is potential energy, and so on. And there's a standard technique that does this, and that's used in many places, called symbolic regression, which does exactly what I just outlined. It discovers an explicit mathematical expression that fits given data. But even if you limit yourself to a limited number of operators and a limited number of terms, you still have an exponentially growing search space. So this is a complicated problem, and it doesn't help if your data is high-dimensional, such as weather observations. The basic way this is done is by putting mathematical expressions into some kind of tree, and then modifying these trees according to some strategy. Often genetic algorithms are used, if you know that term, until you get the best possible fit to your data, and you somehow penalize too many terms or too complicated equations. But that's just what we would ideally like to do. Today, we'll focus on a specific type of these problems, which is still incredibly general and very hard to deal with, namely dynamical systems. So where you have a state x depending on time. This is obviously still almost all-encompassing, so all kinds of differential equations like fluid dynamics or the atmosphere or just the equations of motions fit into this mold. And the data we have is time series data of our system or process at points in time. And obviously, it would be nice to find out the laws behind such a process. But that's an incredibly hard problem, which we'll not solve today. So today we'll solve something different, but that can help us discover equations. So what we want to do today is, from a state, predict the next state. Formally, we want to learn this evolution operator that takes xt to xt at the next discrete time step, which is still complicated. And just as a baseline, before we see the AI-inspired methods in a moment. This is more like a classical method, sparse identification, which has some severe constraints. So it only works for ODEs, where you have both the states and the time derivative, which in practice you can't really measure derivatives, so you need to approximate them. And if you have noisy measurements of x, then your approximations of the derivative will be even more noisy. So this is already a challenging assumption in practice. And this assumes that the function is simple, as we said physical laws often are. So you have a library, might be polynomials, might be sine, cosine. Here the researcher's intuition comes into play. And then they do something called sparse regression, which means fitting your library of functions to the given data using as few terms as possible. So this is something people can do. And the idea behind this and behind almost everything where you're dealing with very complex high-dimensional data is to somehow reduce the complexity. And let's first say what data we're talking about. So this might be sensor fields. For example, in a fluid, you might measure temperature, pressure, wind speed, if you have weather data. It might be videos of some motion, for example. These are obviously all high-dimensional. And a lot of the data you record is redundant or even irrelevant. If you have a video of a moving object, the background doesn't tell you anything. And if you have weather data, big parts of the domain will probably be steady, and you don't need the information at every single point of your domain to make exact predictions. So the key idea is how to break down high-dimensional data into the state variables. You probably have an intuitive understanding of state variables. Let's just look at a very simple example first, the single and double pendulum. How many variables do you need to describe the state of either of these? Any suggestions? How many variables do you need to describe the state of the single pendulum, Leah?
One for the left and two for the right.
If you just want to specify the position, yes, but let's say you have a snapshot and you want to predict what happens next. Then you need not only the position, but also momentum, or the derivative of the angle. So the system on the left is two-dimensional. It lives in a two-dimensional space, and on the right is 4D. Very simple, almost the most simple example you could come up with. Another interesting system is this, which was actually analyzed in a paper. It's like an air dancer. You might have seen them outside in advertising. So this is, in principle, infinite dimensional. This is a continuous shape. It can be deformed at any point in any way. But if you look at it for a bit, it seems somewhat regular. And indeed, you could come up with some clever set of angles and distances so that you can describe every state this thing takes in the simulation with sufficient accuracy. And with the techniques we'll see later, it actually turns out that you need only 8 to 10 variables to get a really good approximation of this. So it's actually not that much more complicated than the double pendulum. So now you might have an intuitive idea of what this intrinsic dimension is, which is the number of state variables, but let's make it a bit more formal. So we have the state living in an ambient space. For example, if we have image data, that's the pixel space. So this is very high dimensional, in this case 10,000 dimensions. But obviously not all images can occur as frames in our data. So the states that actually matter physically form a state space, which is a subset of the ambient space, but much smaller. And you could say that the intrinsic dimension of your system is the dimension of S, And if you don't have an intuitive understanding of that, it's just the number of independent variables you need to describe any state, exactly or within a given accuracy. Let's look at two very simple examples just to deepen our understanding. Let's start on the right. Here, let's say this is a particle in circular motion. Generally, you need two variables to describe its position, x and y. But if you figure out that this is circular motion, then you just need the angle and maybe the speed. But this is actually a particle living on a 1D space, namely a circle. On the left side, it's a bit more intricate because these points almost lie on a line. And it depends on your application whether it's okay to consider this 1D data or not. If the deviations of the points from the line present an error that's acceptable for your application, then you just need the x-coordinate to describe any of these points within this tolerance. Otherwise, you need to consider this still as a 2D data set. So now we have established what intrinsic dimensionality is, and we take a brief detour now, because the idea is our physical system has some state variables which are much less than the dimensionality of the full data, and if we can find out the number of state variables, it might be easier to simulate the system. And this actually relies on a very general idea called the manifold hypothesis, which underlies much of modern machine learning. And it states that natural high-dimensional data lies on a manifold, so a space with certain mathematical properties, that's low-dimensional. And this is assumed to hold for some pretty surprising cases, such as the set of all valid English sentences forms, according to this hypothesis, a low-dimensional manifold in the space of all random letter sequences. Or the set of all images of human faces might be a submanifold of all images. In reality, we know that this hypothesis is not true, but if we extend it to unions of manifolds, there are actually some people who have shown this to hold for very fabricated data, of course, but the success of machine learning nowadays might indicate that this hypothesis is pretty accurate. And this is the case for physical systems as well. Sometimes you can even prove this rigorously, which we'll not do today. And the idea is now to identify the state space. If we know the state space and we can reduce every state into this low-dimensional, easy state space, then it becomes very simple to predict how the system evolves. So we need techniques from manifold learning, which are all about finding this manifold. Just a brief visualization of what we want to do here. This is a data set in 3D. It's known as the Swiss roll. It's really the standard example of this kind of thing in ML. Points in 3D, but clearly they live on a 2D surface that's somehow rolled up in space. Obviously, this is non-linear, but it's still certainly possible to somehow unroll this such that the structure is still the same. Neighboring points on the rolled version still lie next to each other, but it's projected down into the smallest possible state, in this case, the 2D plane. And methods that can solve non-linear problems, such as this one, are, for example, autoencoders, which we'll use today. So an autoencoder looks like this. For our special case, you have the state at one point in time. You plug it into a function called the encoder, and that spits out a much smaller vector called a latent vector. And the latent dimension is small compared to the ambient dimension. And then you plug this latent vector, which you hope contains the important features of your state, into a decoder, which spits out another vector in the ambient space. And the hope is that this is an accurate prediction of the next point in time. The encoder and decoder are general nonlinear functions, which we tune such that this error is minimized. So using the autoencoder to estimate the next step should be as close as possible to the true next step. And now this seems very promising, because if we just reduce the latent dimension enough, we might be able to get it down to the intrinsic dimension. And then we would have found implicitly the state space. And this would look like this. So this is from a pretty simple system. They used three methods. One is PCA, which is linear, so it's expected to do badly, and two different autoencoder architectures. And we have the latent dimension on the x-axis and the reconstruction error, so what's at the bottom here on the y-axis. And we can see the errors decrease of the autoencoders until latent dimension 8. There's one last big drop, and then the error stays roughly constant. So in this case, we would conjecture that the intrinsic dimensionality of the system is 8. And for a very simple system that works, but oftentimes it doesn't work. And you already get big errors for a latent dimension that's orders of magnitude higher than the true intrinsic dimensionality. So even for a system like the single pendulum that's only 2D, you need 16 latent dimensions to somewhat accurately predict the next steps. And reasons for this are, for example, that the manifold representing the state space is somehow complex. On the right here, you see a cartoon of a state space of some system which lives in 3D. Locally, it's 2D, so you have, locally it's 1D, sorry. You have points living on lines, and then at these intersections, it's locally 2D. So in general, this is 2D. And each point, ignore the colors for now, is one state of the system. And you can see that the system has some typical states where a lot of points fall, like red on the left, blue on the right. There you really have points that are dense in the state space. But in parts like green, which might be where a phase transition occurs, you have gaps between the states. So the green part occurs only very rarely in your data. And this means that the autoencoder might fail to know where the submanifold is in that area. So the outline from before, just shrink the latent dimension as far as possible, fails before it gets to the intrinsic dimensions. And there's two approaches I want to present that somehow find a way around this. The first is called neural state variables. It's a pretty simple idea, but works quite well. And this was the paper that inspired me to do this talk. So they train autoencoder, which I call naive here. So you just do what I described before with some latent dimension that's far too big. But then you use these latent vectors, which are reduced approximations, but not in the state variables. And then you train another autoencoder, which seems kind of like a low-hanging fruit, but this actually works very well. And this is able to find out what the true intrinsic dimensionality of many complicated systems is. And then you have found the intrinsic structure, so really the key elements that tell you how the system behaves. And then you can use both of these autoencoders actually to make predictions. So you evolve a few steps using G, and then you use H, which is somehow more stable in the long term, because it really only has the most important information to correct this. And this works pretty nicely. There's another approach that came out roughly at the same time, which is inspired by topology, where they say the domain is complicated, it might not be uniformly sampled, so we will decompose it into different parts. These are called, inspired from mathematics, charts. Here again we have the particle in circular motion. A decomposition into 3 charts might look like this. And before you have a circle, and unrolling the circle into a line is possible, but much harder than taking these circle segments, which are pretty straight already, and unrolling them. And this kind of hints why this decomposition works, because taking a circle segment and mapping it to 1D is much easier. And then you have these segments. Of course, you somehow need to take care of the transitions between segments, but that's not that complicated. And then you can learn the dynamics on each of these charts. So you just have to describe a 1D motion on each and the transition. And this also yields pretty good results. And here, finding the idea is the intrinsic dimensionality is the same idea. So reducing the dimension until it fails. But in this case, this actually gets you down to the true ID, because you have decomposed the domain in some smart way. Let's compare these two approaches. So this is a reaction diffusion, PDE, which is actually what I'm doing my bachelor's thesis on. You have 2 components. You just look at one on some spatial domain. And this is, in generally, a very hard PDE to analyze because it's chaotic. Small changes in initial conditions lead to big changes in outcomes. But if I show this again, here it seems very periodic. And this is indeed a limit cycle, which is an important concept in the theory of dynamical systems. Here, each of these arrows is a different initialization, but all of them converge. So this is some representation of the state space, converge to one cycle. So even though our PDE solution is infinite dimensional, or if you discretize it, it's at least very high dimensional, in this case, we know analytically that what we saw before lives on a 1D manifold in its high-dimensional ambient space. And the question is, can the methods we just saw attack this? And it turns out to some extent. So on the left side, you have the true evolution. The 2 in the middle are from the neural state variables approach, the first approach, with latent dimensions 2 and 1. And for latent dimension 2, you get a good approximation. But for latent dimension 1, you get artifacts. So it's kind of close, but far from perfect. And on the right, you have the second approach, which for dimension 1 works perfectly. Because apparently, this spiral lives in such a complicated space that it's not possible to approximate it naively just using 2 autoencoders. So far, so good. We can take such a system with high-dimensional input and be able to predict how it evolves. And we know the intrinsic dimensionality of the system. But there's lots of things we don't know. For example, the state variables we discover are not unique. Anytime we run the algorithm, we get a different set, a different solution. And this is even baked into the physics, because you might describe the pendulum with angles and velocities, or you might use kinetic and potential energy. So there is not one correct set of state variables. And this translates into our method, but it's even worse, because these are not really physical variables. They don't have units. They're just abstract mathematical coordinates that are good enough to describe what the system does, but our goal from the beginning to make things intuitively understandable has somehow failed. And it's pretty much impossible to translate them into physical units, We know the correct number of variables, but we have no idea how they relate to the quantities we know from reality. Sometimes you can do this mapping. That's still an active topic of research, but it's pretty much not the goal of this method. Then you might ask, what did we do all this for anyways? Well, if you know the idea of a complicated system and it's lower than you expected, that might tell you that you have some conservation law or some constraints that are not obvious at first sight. So it reveals some properties of the system. And obviously we can pretty efficiently predict the next step if we use the low-dimensional state space for predictions. And this can save a lot of computational power compared to simulating the thing in its full high-dimensional space. And there's some nice ways of using the ID. For example, you can guide a method like symbolic regression with some constraints that somehow push it towards solutions that respect the intrinsic dimensionality. And it's useful for data fusion. For example, in weather data, you might have measurements from stations at the ground and satellite data, and you somehow need to find a compromise between them. And if you have estimates of their dimensionality, you can quantify how confident they are, and you can find better things than, for example, just averaging. Okay, we're almost done. Let me give a brief recap. So we find the intrinsic dimensionality of complicated dynamical systems. The existence of these manifolds is sometimes guaranteed by a rigorous derivation. Often we assume the manifold hypothesis holds, but this works in a large number of cases. We saw two techniques that get around the problem that autoencoders by themselves are not powerful enough. And we can't really interpret this very well, but we have a way of efficiently simulating a system. Okay, that was my talk. Thank you very much for your attention. Do you have any questions? I guess at the moment it's mostly theoretical. So in the last years, there hasn't been that much in the literature actually using this for practical things, unfortunately. I actually don't know either. It's a mathematical structure with some nice properties. So it's not too complicated. You can always map it to some real valued vector space, at least locally. So for like the single and double pendulum, you could go down to 2 and 4 and make accurate predictions. And for example, for the air dancer we saw in the beginning, it was somewhere between 5 and 10 that it worked.
So there's usually like an equation to calculate how many dimensions?
Yeah, for like simple things like the pendulum, you know it a priori. For more complicated things, you have no idea. And you can just say, if we're able to predict correctly, we can't be that far off from the correct number of state variables. Always no, because life is not that simple. But for the example in the paper, they usually got there or close.